Welcome back to enthalpy. We've discussed using bond breaking and forming, so figuring out what the compounds look like, the structural formulas, to calculate the amount of energy involved in a chemical reaction. But that's hard. That's a lot of drawing, a lot of counting. Isn't there some way easier? Why, yes, Susie, there is. We can use what we call heats of formation or enthalpy of formation. And I've seen it written this way, I've seen it written this way. Just know there's a little F, okay? Heat of formation. And what that refers to is the energy that is either released or taken in when 1 mole of a compound is made from its elements. So this right here we know that balanced it's this way. Well, heat of formation is if you have 1 mole. So 1 mole, we'd only use half a mole of oxygen, and we can do that if it's moles. We can't do it if it's a molecule. There is a heat that we can calculate what will be released when that reaction occurs, and that will be called the heat of formation. For that, you're going to need a table, and I have tables in my classroom that you can use to just kind of give you an idea here real quick. Here are some substances, energy, enthalpy of formations for different compounds and elements. And you'll notice, I'm going to go ahead and zoom again, maybe. You'll notice here, this very first one, silver, has a heat of formation of 0. Anybody want to take a guess why? Could it be that elements are elements and you don't have to form them? That's what you said. You're right. So, if it's an element, it's not going to have a heat of formation. Unless, oh, you knew that was coming, didn't you? Let's see. No, I knew I did that. I was just messing with you. All right. Okay, it's going to be in its lowest state for an element, unless, for instance, here's the example. Bromine occurs as a liquid at room temperature. It will change to a gas very easily, but it takes a little bit of energy from the air. Notice, bromine liquid has an energy of 0 kilojoules per mole. All right, but bromine as a gas, the enthalpy of formation is going to be 3.1 kilojoules per mole. So it's going to take a little bit of energy to make bromine become a gas. Carbon, when it's in its graphite form, like at the end of your pencil or what's in the little spray can when you make your Pinewood Derby car, graphite has a heat of or enthalpy of formation of 0, but a diamond, still carbon, but a diamond is much more complex because it's a crystal, so it's taking more energy to put in. So if we were to try to go and pull the diamonds apart, it would take more energy. So it has an energy of 2.9. Okay? Here's another example with iodine solid and iodine gas. All right, well, enough about that. Back to our show. It's not really a show. This is different from bond energies. This has bothered me for a while, but I'm finally good with it. Okay, bond energies, you break the bonds, and then you subtract the bonds that form. But here, we're talking about, somebody's already done all that calculation for us. Okay? You will get a table that is going to have bond heats of formation on it, or enthalpy of formation. For instance, this little table has calcium carbonate. If you have a mole of calcium carbonate, you're going to have a heat of formation of 1209.6, a negative heat of formation, calcium oxide, and carbon dioxide. What we're going to do is we're going to switch things up. We're going to put the sum of the products minus the sum of the reactants, whereas before it was reversed, but that was bond energies. Now we're talking about whole compounds. No more worrying about the whole reaction and breaking and all that stuff. Okay, let's look up here. My reactants are calcium oxide and carbon dioxide. Calcium oxide has a heat of formation of negative 653.1. Carbon dioxide has a heat of formation of negative 393.5. Now, the other piece then is going to be look at the reactants. And our reactants is just calcium carbonate, and his heat of formation is negative 1206. But remember, it's minus. Products minus reactants. Products minus reactants. So when you subtract a negative number, what do you get? You get a positive. So we're ultimately going to take negative 393.5 plus negative 635.1, and we'll get 1028.6, and that's a negative, plus 1207.6. Make sure I did that right. 393.5 plus 635.1. Look at that. I did. So we're going to take that to negative number. I'm going to start here just so that I don't have a problem with negatives and positive. 1207.6, and I'm going to subtract that from him. And we have a, that didn't work very well. 127.6 minus, oh, what have I done? Let's start over. 7.6 minus 1028.6, 179. And it's a positive value. That is the energy that is going to have. Now, that's a positive number. Positive enthalpies come from endothermic reactions. So that means to get this reaction to occur, you're going to have to add energy to it. Okay? We're not going to add stoichiometry today. I do want to do another example, so hold still for a minute. All right, awesome. So here we have two reactions. Remember, we're going to do the sum of the products minus the sum of the reactants. My products here are sodium chloride and water in the gaseous state. Does that make a difference? Yes, it does. So I'm going to start with the sum of my products. Sodium chloride, NaCl, help me look for it, on there twice for whatever reason, is negative 411 kilojoules per mole. And I'm going to add that to gaseous water, which is negative 241.8. That kilojoules per mole. So if I do 411, and they're both negative, so I can just add them regularly. 241.8. I get a total for my products of 652.8. So I'm going to write that under here. 652.8, and it's negative. Okay? So there's my products. I'm going to erase this. I don't necessarily recommend you do that, but I don't have a whole lot of room, so that's why I'm doing it. Now my reactants, I have sodium hydroxide in the solid form and hydrochloric acid in the gaseous form. So here we go. Sodium chloride or sodium hydroxide, NaOH, in the solid form is negative 426.7 kilojoules per mole. And our hydrochloric acid in the gaseous state is negative 92.3. If we add those together, we get negative 519. So we're going to subtract negative 519. Two subtractions you add. So we're going to have 519, because it's now positive, 519 minus 652.8, and that gives us a negative 133.8 for our total. Okay, let's try the next one. We've got 2 carbon dioxides in our products, so we'll start with products. 2 carbon dioxides, carbon dioxide right here, negative 393.5 times 2. 393.5 times 2 gives us negative 787. Okay, we want to subtract our reactants. We've got 2 carbon monoxides, negative 110.5. $221. And then we have oxygen. What did we say about oxygen? Anything in an elemental state. If it's in its most stable state, it'll be 0. So we have 787 minus a negative 221. Once again, 2 negatives make a positive. 221 minus 787, negative 566. All right, so now you've had that introduction. Where's my stop button?